left off, or no, not last week, 2 weeks ago, I guess. When we left off 2 weeks ago, we were talking about oscillators. And we went through the basic oscillator using an op amp and a lead lag circuit. I went through all that. Yeah, don't look up. So there are other types of oscillators we can use. So one type basically involves using my op amp and feeding back through 3 RC filters. Now, this is a fun part here. And I can do this either way, all right? I could have RC, 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 or I could have CRC, RC off. What's the difference? Well, for this type of circuit, in general, and we covered this a little bit, but just to remind you, if I just look at one of these filters, we know that this is a low-pass filter. But there's something else that happens, right? We went through the whole, process of figuring out how much the signal was reduced, came up with that formula way back in chapter 14. The part we didn't talk about too much is that in addition to filtering, it also creates phase shift. Now, the phase shift for a circuit like this is basically what we're looking at is, we're going to have a current that becomes leading. So we're going to end up with some angle of leading current. And then we end up with taking that current across a capacitor that causes a phase shift between the current and the voltage. And since I ultimately want the voltage out, what this is going to do is create a lagging output. And that is because if I take a current with a positive angle, multiply it by capacitive reactance that has a negative 90-degree angle, well, now we end up with a lagging output voltage. So what I do is I create the RCs for a frequency. So I basically want a frequency that creates a negative 60-degree phase shift. Now, why? Well, I have 3 of them. 3 times negative 60 is negative 180 degrees. That's inverting. Note that the input from that circuit goes into the inverting amplifier. And so now if I invert and invert, what am I back to? I'm back to the original, which means at that frequency, I have positive feedback. Any other frequency other than this, I don't have positive feedback. So that's basically the idea of how that's going to work. If I switch the position of the resistor and the capacitor, it becomes a lead. And I do the same thing. 3 times a 60-degree phase shift is 180. Well, 180, negative 180 is the same thing. Make sense to everyone? That's one RC oscillator. Real quick. Another type of feedback circuitry. I think I drew the whole circuit up when I I'm going to find my book here. I'm lecturing without my book. Okay, there we go. So another type of feedback when we were in the chapter 20, and we had our notch filter, right? So if everybody remembers that notch filter, we had this twin T type of circuitry, right? Where you had like a multiple feedback path with capacitors and resistors that were half the size of the regular values and everything else. So suffice it to say, what that did was that created a notch, a reduction in the feedback. Right? So with a twin T oscillator, I basically set up the same thing that I had before, except now I run that into the inverting input. And so, and I kind of set up the same thing I had before with the whole gain thing using a lamp, right, for the variable part there. And I'm not going to redraw the whole circuit. But what this creates at this point is essentially a frequency response. Looks like that. So what are we doing? Well, we're providing negative feedback everywhere but that frequency. Okay. So it's like the opposite effect. So not only is there a dip there, but there's also a phase shift that ends up being zero at that point. And so you get no negative feedback at your resonant frequency. So all of these circuits are using resistors and capacitors to do the work for them. But that's usually going to limit me. All right. So RC oscillators are generally limited to about 1 to 2 megahertz. Do the math, it's just because capacitors end up being so small, the resistors have to be big enough. And it's 1 over 2 pi RC for a lot of these formulas, or something close to that. So we're limited. So where do we go from there?
Well, you're saying that the output of this oscillator is limited somewhere between 1 and 2 megahertz. You can't do a 500 kilohertz very well.
Oh, no, that's the upper limit. I'm sorry. Yeah. So upper limit. Oh, no, you can go as low as you want. Well, not as low. I mean, pretty low. You can go pretty low. So for those of you that built trainers, the function generator in the trainer is a 2206. And I think that's actually covered in this chapter. I don't cover it, but if you want information on it, it is in it. But that uses a RC network to create frequencies. And so your function generator, for those of you that build it, generally the upper limit's around 120 kilohertz just for their design, but it goes all the way down to 1. I guess if you wanted to make it higher, I don't know, for the 2206, I'd have to look at the specs and see what their recommended maximum is.
And then this twin T filter.
Yeah.
What is its function?
Well, it's the one that we for the notch filter.
Okay.
Kind of looks something. I can't remember. He's got it in here. I got to look at it to remember.
So I'll just pass most everything except for.
Yep.
Yeah. So
it looks something like this, I think. Anything, something like that. That was the twin T filter. So we come in there. I know we've got it. Oh, there we go. Okay. Yes. I got slightly low. I haven't built one of these before. So this is basically D in, and there's V out. And that's the response. So it creates a notch. And so because that's feeding back to the inverting input, I get lots of negative feedback up there, none there.
you wanted to tune that, just a variable oscillator, or
Well, you would have to have variable resistors, and they would have to be ganged. Yeah. So these type of filters are not very good for a variable. Anything that, same idea here, right? If you want to have this vary, you'd have to have all 3 of them changing together. So the better type of filter is one where you only have 1 resistor and 1 capacitor, creating that frequency, if possible. And I think
You don't need to change either R or C, you don't need to.
Correct. Yeah. In fact, well, like for example, for your function generator or the function generators that you built, for your trainer, what they do is they have the capacitors are changed by the switch. And so you have capacitors that change by factor of 10, and then you use a variable resistor to change R, and that gives you the fine tuning. So you're changing both. You're using one for coarse, one for fine. And that uses the 2206, which does use just a single resistor and single capacitor to set frequencies.
If you're using this for a radio receiver, you want to eliminate interference from a particular station, then you probably only need to use either the R's just to get a small.
Yeah, if it's a fairly small range. Okay. So how do we get above that frequency?
What?
Oh,
Does that circuit, that notch filter have a Q? Can you make it a narrower Q?
there is a Q associated with it. He doesn't go into the Q in this circuit or in this chapter, but I believe when we used it as an active notch filter, there was a Q associated with it, which I believe because he used the feedback path and voltage gain to create it. The Q, when you use an op amp with voltage gain, which is technically what that circuit is, the Q is equal to 0.5 divided by 2 minus the voltage gain, where the voltage gain is just R2 over R1 plus 1. So that is back on page 840 of the text. Essentially this circuit. But now, it's a little bit different because of using this part here with the feedback.
You want a very high Q, you want a low denominator. So you have to try to set your A sub B to be very close to 2.
Which would require precision resistors probably to make sure you don't go beyond that. All right, so how do we get above 2 megahertz? Well, now we're going to get into LC. Typically an LC tank circuit. Or in general, LC oscillators. So the same concept that we had last time, the same general concept is going to hold true. All right, we're going to have an amplifier. So we start with a basic amplifier. Nice common emitter amplifier here. Now, one thing that is typically done with LC type of oscillators, instead of having a collector resistor, we actually end up with a choke. Okay? Choke is just another word for an inductor. All right, so we're looking for something that is going to create, a much higher resistance or opposition to current flow at higher frequency. So then we complete our common emitter amplifier. So that's our amplifier. Now, it's going to have a gain. Remember, we want a gain feedback constant greater than 1 at startup, equal to 1 when operating. So we take our output, and for this type of circuit, we're going to put 2 capacitors in series, and then those 2 capacitors are in parallel with an inductor. Look at my labels right here. C1, C2. Right? Now, between those 2 capacitors is my reference point of ground. And then take the voltage here and feed it back to there. Now, the output voltage, I should label that. There's your output voltage. So the way this is set up, and we'll just, I'm going to put polarity markings on here, just assuming our positive half cycle. So on the positive half cycle, with respect to ground, the output is positive. Now, because these two capacitors are in series, they're going to have the same current. Any current going in, charging that up and down, is going to create the same polarity across the lower capacitor. So you'll notice that with respect to ground, the feedback across C2 that comes back to the input is inverted with respect to the output. What does a common emitter amplifier do to its input voltage? In addition to making it bigger, it inverts it. So twice inverted, I get my original back. That is my positive feedback. So this would be the output voltage. This would be my feedback voltage. Well, because they're in series, they're going to have the same current, right? There's a circulating current in here, going back and forth, oscillating back and forth. So the voltage, the feedback voltage, will basically be that current times the capacitive reactance of C2. The output voltage would be whatever that circulating current is times the capacitive reactance, C1. The feedback fraction is just defined as the feedback voltage divided by the output voltage. So when I do that, the feedback voltage is, and you notice when I do this, the currents are going to cancel, right? So it'll be 1 over 2 pi frequency times C2 divided by, again, the currents cancel out, capacitive reactance of C1 is 1 over 2 pi frequency C1. Well, 2 pi f cancels out. And I have 1 over C2, and then the inverse of 1 over C1 is C1, so this just becomes C1 over C2. That's your feedback fraction. So what's my minimum gain? Well, it's 1 over that, which would just be C2 over C1. And here's the fun part. What is the resonant frequency of this tank circuit? All right. If you go back a ways, right, we've discussed our center resonant frequency for tank circuits way back at the end of EET 125, if you haven't seen it since. I know that was a year ago. All right. Well, it's a fairly simple formula. 1 over 2 pi square root of LC. But I don't have one C, I have two. So when capacitors are in parallel, they add. When they are in series, how do they combine?
Like parallel resistors.
The formula is the same as parallel resistors. So for two of them, product over the sum. So the capacitance in this circuit then would basically be C1 times C2 divided by C1 plus C2. And that would be your resonant frequency. Okay. So all those formulas are next to the circuit. This circuit is referred to as a Colpitts oscillator. That's the guy that designed it, figured it out. Okay. Now, there are different ways to do this in terms of providing my output. All right. That is an inductor. If you make that inductor part of a transformer, you can take the output off of that. All right. You can use a capacitor to couple from the output voltage to a resistive load. All right. So there's different ways we could do that. Right. So if this inductor is part of a transformer, boom, there's your output. Right. Or we connect the capacitor to the load resistor, whichever, whatever, different ways to take it off of this. If I change this to a common base amplifier, and I'm not going to redraw the circuit. He has it in the book and everything. But if I change this to a common base amplifier, basically what I can do in my feedback loop is ground is here. There's your feedback. Feedback voltage is right there. Okay. Now, how is this different? Well, again, my output voltage is actually for C1 and C2, both voltages. So if I look at my positive half cycle, the feedback is positive with respect to ground or in phase. And remember, common base amplifiers do not invert. So no inversion feedback, we're good. The only difference now is the feedback voltage and the output voltage, C1 and C2, are set up like that. And so the feedback voltage basically becomes the output voltage times capacitive reactance of C2 divided by the capacitive reactance of C1 plus the capacitive reactance of C2 because they are in. So this becomes my feedback fraction. And then if you do the math on that, 1 over 2 pi f C2, 2 pi f C1 plus 1 over 2 pi f C2, right? That's basically what that is. And so again, all the 2 pi f's cancel. So now we have 1 over C2 divided by 1 over C1 plus 1 over C2. And if I multiply this by C1 times C2 divided by C1 times C2, right? It's 1. I haven't changed anything. 1 over C2 times C1 over C2 cancels out to C2. And I have C1 divided by C1, C2 here becomes C2 plus becomes C1, or this is the sum. So it's C1 divided by the sum. So your feedback fraction does change a little bit. Instead of C1 over C2, it would be C1 over C1 plus C2. Those capacitors are still in series, so the resonant frequency calculation and everything stays the same. Slight change.
The advantage of this connection.
Just a matter of which amplifier you want to use. Common emitter or common base. We need voltage gain either way, right? So what's one thing we cannot use? Cannot use a common collector amplifier because it does not have voltage gain. And then he also shows a circuit using a JFET instead of a transistor. Now, here comes, I don't know, different ways of doing this, right? So the general setup, amplifier, feedback network. Okay, amplifier, feedback network. So, other ways we can do this. I'll just go through a few of them here. And then we'll take a break. So in this case, the feedback was basically a voltage divider made up of 2 capacitors. Well, what else could I do? How about a voltage feedback network made up of 2 inductors, right? We'll do the exact same thing we did here. Common emitter amplifier. And now, instead of 2 capacitors dividing the voltage, I use 2 inductors. I think there's oh, there it is. Okay, yeah. Set up the same ground here. A feedback still comes back here like this. I just have 1 capacitor. Now I have L1, I have L2. Formulas do change slightly because, again, this is my feedback voltage. Here's your output voltage. Plus, minus, plus, minus. It's inverted into a common emitter amplifier. So that all works there. Feedback fraction here, of course, is going to be what? voltage is determined by the same circulating current, but the reactance that the feedback voltage is developed across is 2 pi FL2, and the reactance for the output voltage, 2 pi FL1. Feedback fraction is L2 over L1. A reverse. Because of that formula for reactance. And inductors in series, how do they combine? Just like resistors. So they add. So you still have your same resonant frequency formula, 1 over 2 pi square root of LC. L being L1 plus L2. They just don't. So all I did was switch out 2 capacitors, and I used 2 inductors instead. And now this becomes known as a Hartley oscillator. A Hartley oscillator. Another way to do this, small one here. So same general concepts here, right? Common emitter amplifier. And now, put a capacitor and an inductor, technically not an inductor, more of a transformer. And here's the key. The phasing dots are such that if I have an L, I have a C, so we have our same resonant frequency formula. But now I use the secondary of a transformer to provide the feedback. The phasing dots are opposite, so that on the positive half cycle here, the output is reversed, and I'm feeding back the inverted signal. The feedback fraction now becomes a matter of the transformer interaction. All right, he defines it as M over L, whatever M is, which is like the mutual inductance side. Okay. So when I do that, using essentially a transformer to provide the feedback, this is an Armstrong. Wait, there's more. You've noticed that all these formulas so far have had a lot of interaction of the parts, right? Where my C1 and my C2 not only affect the feedback fraction, but they also affect the resonant frequency. So kind of annoying. So what I do, here, let me just go ahead and modify this one. So what we do with our Colpitts oscillator is I make one slight change. I add in C3. Now, by adding in C3, note that the circulating current means that the total capacitance technically will be the inverse of 1 over C1 plus 1 over C2 plus 1 over C3. C1 and C2 still provide that feedback fraction. Okay. So we end up with C1 over C2 still, because that's where the voltage is being divided. But here's the key. We make C3 much smaller than C1 and C2. So because this formula is the same as resistors in parallel, if one resistor in parallel is much smaller than all the other resistors, the total resistance is going to be what?
less than the smallest.
It's going to be less than the smallest one, but if this is a lot smaller, it's going to be very close. So now the capacitance that we use here is going to be approximately C3. So now I can set the frequency using C3, set my feedback fraction using C1 and C2. When I do that, this becomes a flat oscillator. So far, so good. Going to make it one better. All right. So the combination of L and C3 set my frequency. If I simply replace those two with a thin piece of piezoelectric material. Oh no, who got that?
You did it. But it was in the middle of you talking, so and I looked at her and I was like, it's all you.
Piezoelectric material just means what? Material that under certain circumstances will vibrate at a certain frequency and produce a small electrical effect. In other words, a crystal. When we put a crystal in here, now crystals are designed to resonate or have a resonant frequency based on the material and the size that they are cut to. And we can get very, very precise frequencies and very, very high Qs. Typical crystal materials, quartz. Well, it's been too long. Got it. What do we got? Quartz. Rochelle salts. One finally came to me. Salt. And tourmaline. These are typical use crystals. The most common one you probably hear about is quartz. Quartz is provides a good frequency range. The thinner the material, the higher the frequency. So you get limits to how thin the quartz can be, which limits your upper frequency. Tourmaline can be cut thinner and still work. So that's how you get your really high frequency crystals. Rochelle salts have a relatively low electrical output, so not as good. They can be used for other things. Okay. The quartz by far kind of falls right in the middle of that. Fairly high electrical output, fairly high frequency range. Typically. Go ahead and take a break. We'll take a break till 10 till the hours. We'll come back at 5 till. And see what else we want to talk about. I got a few things. So any questions on LC oscillators in general? Right? I know I went through a lot of them and everything, all the diagrams, they're in the book. Okay. So that's, you can always go there and look at that. Yes, sir.
Well, the book says that you get high stability accuracy with quartz crystal oscillators.
Correct. So by stability, what they mean is like temperature stability and high accuracy, because inductors, capacitors, just like resistors, have tolerance. And so getting the exact frequency can be a little bit tricky. So with a quartz,
So you get drift with.
and you get drift with temperature, age, all kinds of.
You'll get less with the crystal.
Correct.
And now
And
you have to find the crystal with the right frequency.
correct. or select the frequency you want and multiply it. You get a higher frequency out by using a Class C amplifier as a frequency multiplier. Start with a crystal frequency that's lower and create something higher.
And then you introduce some drift with that amplifier.
Not as much. Not as much, because remember, the output of a multiplier is based on the input. As long as you're fairly close to the, for example, let's say you want to triple it. The resonant frequency, when you do your tank circuit, you're going to get a response like this. But if you have a crystal input that provides a very precise frequency, so whatever the frequency of the crystal is, times 3, that's going to be your output. That's the whole idea of a multiplier circuit. If you don't get the center frequency, you get 3 times the input frequency, as long as it is within that range.
But wouldn't you be using components that have temperature drift?
Well, yeah, and if this drifts a little bit, so if this drifts a little bit like that, don't care. Still getting 3 times that crystal frequency.
Get the impression that crystals are used less often.
Yeah, because we have something called a phase lock loop. But those are still going to be used. A lot of those are still going to use crystal references.
You can modify your phase lock loop with one crystal, you can get a whole bunch of different outputs.
Exactly. Exactly.
Are we going to study phase lock loop?
I cover phase lock loops in wireless communications. I think it is in this chapter as well. I don't think I'm going to have time to get to it today. But I do talk about it in wireless. All right. So those are my LC circuits, right? And all the way up to quartz. So the next thing I want to talk about here is actually going back to RC. That is now, it's a chip. So what we're going to talk about now is a 555 timer. So the 555 timer is an 8-pin integrated circuit. A simplified block diagram of this is right here. So we have comparators. Everybody remembers our comparators, wasn't that long ago, right? This is an SR flip-flop. Now, everybody in here has had digital, I hope. I think so. Been a while for some of you. But an SR flip-flop, remember, set, reset. So when the set input is activated, Q goes high. When the reset input is activated, Q goes low. This has 2 outputs, Q and not Q. So not Q is just the opposite of Q. You're either high or you're low. Now, VCC is applied here. A pin 8. Ground connection is pin 1. Now, it doesn't show it. This is a simplified diagram, right? But VCC is also going to power your comparator, is going to power this, right? No surprise there. But what we see here between pin 8 and pin 1 are 3 5K resistors in series. So series resistors simply form a voltage divider. So what do we have right here, this point, which is defined as the upper trip point? Well, 5, 5, 5, the total is 15. From ground to this point, 10 divided by 15. 2/3 of whatever VCC is. That's my upper trip point. The lower trip point is across 1/5K, so 5 divided by 15, 1/3. So I have two trip points, 2/3, 1/3 VCC. Now, for this one, the upper trip point is on the inverting input, and then the other input is called threshold. All right, so that's my pin 6. So when I get above pin 6, what's going to happen? I'm sorry, let me rephrase that. When pin 6 gets above the upper trip point, we activate the comparator, which activates the set input, which makes Q go high, not Q goes low. Well, Q goes to the base of an NPN transistor. So what that is going to do is turn this transistor on and provide or make pin 7 essentially connect to ground. Now, when my trigger, which is the other input to the lower trip point comparator, when the trigger input drops below the lower trip point, that activates this comparator, which activates the reset input, which makes Q go low. So when Q goes low, what happens to this transistor? If I put 0 volts into the base of the transistor, that transistor will be off. All right. Now, and then we do have the ability, an external pin 4 allows me to reset that flip-flop. All right, so if I reset the flip-flop, that basically makes Q go low, not Q goes high. So I can basically force the output high at any time using that input. Now, you'll notice that there's another pin here. I've talked about all the pins, but pin 5 here. Now, pin 5 is called control, and it basically accesses or connects right to the upper trip point. This gives me the ability to, with an external voltage source, change the upper trip point to something other than 2/3 of VCC. We'll talk about that a little bit later. The typical ways that a 555 is used, the two most common ones are what are known as a monostable or monostable operation and astable operation. So monostable operation means what? One stable point. Typically, the way that is done is I use pin 2 as a trigger, and then what will happen is the output will change on that trigger for a set period of time and then go back. So I can basically create a certain width of a pulse using that trigger. It's only one stable operation. It stays in that stable operation until I trigger it. It gets unstable. In other words, it changes for a set period of time, goes back. Astable operation means what? It means it is not stable. That is an oscillator. That's how I create an oscillator. So let's take a look at how to build those two circuits. We start with the astable. The basic idea of my astable operation is I'm going to take my VCC, resistor here, capacitor there, right. Go ahead. Make sure we all know that's that. My discharge connection goes right here. My capacitor goes to pin 6, the threshold, and the trigger, which are basically the two inputs to my comparative. I just want to get my labels correct here. R1, R2, C. Okay. So this is R1, R2, and capacity. Now, what's going to happen here, if we look at the voltage across the capacitor as a function of time, we have an upper trip point and a lower trip point. So let's just assume, all right, that the capacitor voltage starts right here. Now, what has happened right at this point is that I have reached the lower trip point. And what happens with the lower trip point? When I reach the lower trip point, we reset. Q goes low, so this path here does not exist. Not Q goes high. So if I look at my output voltage, it went high. Now, because this path does not exist, VCC is going to provide a path to charge my capacitor toward VCC. The capacitor starts charging. VCC, of course, is up here. So it starts charging toward VCC until it hits the upper trip point. What happens then? Well, when I hit that upper trip point with that capacitor voltage, this is activated. I set, which means Q goes high. So when Q goes high, this point is essentially connected to ground. And now the capacitor starts discharging, which means the capacitor voltage starts to drop. Where is it dropping toward? Ground, which is 0. So it starts dropping. When it gets to the lower trip point, starts all over again, right? Charge up, drop down, up, down. Okay, and of course, when I reach that upper trip point and start discharging, because Q goes high, not Q goes low. We have an output, essentially a pulse wave. So when capacitor is charging, we are charging through R1 and R2. When I am discharging through R2. Now, this is important for my calculation. So the fun part, and I think I went through this with the analysis of the relaxation oscillator that we covered back in our nonlinear op-amp circuits, and I put up the whole charging thing and everything else. I'm not going to go through all that again because this one's a little simple, all right? I start from 1/3 VCC, and I'm charging up to VCC, but I only get to 2/3 VCC. So I only get halfway there. So if we go on to our charging, our universal time constant, and say, how long does it take to get to 50%? That time period, all right, so basically time to 50%. That's what we're doing, right? We're going from 1/3 to VCC. Halfway there is 2/3. When I'm at 2/3 VCC, I'm going down to 0. Halfway there is 1/3. So it's the same both ways. And that time is 0.693 times the time constant, which is R times C. So my discharge, my charge time, charge time is basically going to be R1 plus R2 times C times 0.693. The discharge time will simply be R2 times C times 0.693. Make sense to everyone? Well, the frequency is 1 over the period. The period is the sum of those two. So when I add these two together, the period for this circuit is 0.693 times C times R1, R2 plus R2, so add 2 R2. So this is your period. The frequency is just the inverse of that. Make sense to everyone? Now, if you wanted this output to be a perfectly 50% duty cycle, to where the charge time and the discharge time are the same, mathematically, R1 would have to be 0. Is that a good idea? At the same time that I am discharging the capacitor through R2, I'm essentially taking this point to ground. You do not want R1 to be 0. Okay, so you're not going to be able to get a 50% duty cycle at all. Okay? The charge cycle is always going to be a little bit longer, or the charge time is always going to be a little bit longer. While I'm charging, the output is high. So the duty cycle will always be 50+%. You can get down close if you want to, I guess. But keep in mind that the smaller R1 is, the more current you're drawing during that discharge time. So not really a good idea to spend too much time. Make sense, Deborah? Go ahead.
I think that T equation is wrong. The book says that it's 0.693 times the sum of R1 plus 2R
That's what I have.
times the capacitor.
2 times R2. R1 plus 2 times R2, 0.693.
Yeah.
Yes.
I just took it the wrong one.
Oh, yeah. That's the general form that I took from here to there. All right. Now, make sense to everyone? So here's the fun part. So notice that I did not use pin 5 here. Pin 5 gives me access to the upper trip point. So what happens now if I were to say, for example, change that upper trip point? Let's say I lower it. Well, what's going to happen? I'm going to reach that threshold sooner. What have I just done to my output frequency? Higher frequency. If I go above, it'll be lower. What I have just created is a voltage-controlled oscillator. With the control, I can create a voltage-controlled oscillator where now I can use an external voltage to change the frequency of my circuit, or of the output of my circuit. He actually goes through and does the whole derivation of the formula, which is, I'm not in the mood for it. Okay. I want you to understand the concepts. Right? That's the important. I also mentioned that this can be used for what is known as monostable operation. So for monostable operation, circuitry changes a little bit, but not too much. So basically what I do for monostable, any questions on all this? All right. So for monostable operation, pin 2 is my trigger. So pin 2, whatever the voltage coming in here is, what I have to do is provide an input voltage that is basically low enough to reset this output. All right, so under normal conditions, all right, the output is low. This is my output. Starts off low. So because this is low, the output is low, that's not Q, that means Q is high, which means this path here is grounded. So initially the capacitor voltage is 0. That's a stable condition. Okay. Now, when I trigger here, so this has to be less than 1/3 VCC. Oh, this is all. Okay. So now, when I trigger this, all right, so if I get below 1/3 of VCC, this just could be a very short, brief pulse, just enough to activate that comparator, reset. So now, when I reset, Q goes low. Not Q goes high. Because Q goes low, this transistor is off. And what happens? Capacitor starts charging. So the capacitor voltage now, until I triggered, was at 0. So what's the capacitor going to try and do? Well, through R, it's going to charge up toward VCC. But when I reach the upper trip point, what happens? I forgot to. I'm sorry. I forgot to connect that one. Sorry about that. Okay. So the capacitor voltage is tied to pin 6 as well. So now, when the capacitor voltage reaches the upper trip point, this comparator is activated. We set, which makes Q go high, which turns this transistor on, and it makes the output go low. So while this capacitor is charging, the output voltage is high, and then it goes low. Back to my stable condition. And I sit there waiting for my next trigger. Now, the amount of time, right, the pulse width, determined by how long it takes to charge from 0 to 2/3 of VCC. So maybe I will go ahead and I want to see, that was 2 weeks ago, right? Yeah, we had that universal time constant curve up. Let's see if I can find it here real quick. Oh, there we are. Perfect. Okay. So now, this is my curve. We're going to go from 0 to 2/3, which is 66 point, lots of sixes, right about there. That takes about, boom, right there, 1.1 time constants. With the pulse width then, So my pulse width ends up being RC, which is the time constant, times 1.1. And of course, what we see too is that when we trigger that, this transistor turns on. There's no resistor in here to limit the rate at which I discharge the capacitor. So it's a very quick response, very quick recovery, so that I'm very quickly back ready to start that process again as soon as I have another trip. Monostable operation. Fun times. It's a nice little device, right? Very, very handy. You know, it's got a lot of flexibility, a lot of capability. You can go ahead and get a 556 timer. 556 is just two independent 555s on the same chip. Different ways you can play with that.
Why do you call it, what is the function of it? You just want to generate like AC signal,
I'm sorry, say again.
you just want to generate.
Well, what this will do is this will generate a fixed width pulse. So what I can do, all right. So let's say, for example, that I set my pulse width to 1 millisecond. Okay. I'll go ahead and turn this off. So what I can do with this pulse width is, for example, if I were to trigger this with a frequency, so remember our pulses that we had? You know, you can generate pulses different ways, all right? So if I were to set this as a frequency of 500 hertz for my trigger frequency. Now 500 hertz is 2 milliseconds between pulses. So I trigger it, I get a 1 millisecond pulse out. That means I'm off for 1 millisecond, trigger it. Go. So what I've just done is I've created a 50% duty cycle output from my timer. Well, let's reduce the frequency down to 200 hertz. That means there's now 5 milliseconds between pulses. So I trigger it, I get my 1 millisecond pulse, 4 milliseconds off, right? And then boom, I get another 1 millisecond pulse. I've just changed my duty cycle to 20%. If I were to increase the frequency to, simple math here, 800 hertz, that means I'm pulsing at every 1.25 milliseconds. If I'm on for 1 millisecond, I'm off for a quarter of a millisecond. On for 1, off for a quarter. Now my duty cycle is I think 80%. Can't do math fast in my head, but you know, so I've got about an 80% duty cycle. Now, what can I do with that? Well, everybody in here's had power supplies, right? Almost. Everybody? I think so. Remember that one of the things that I can do with a variable duty cycle waveform is filter it and get the average. Okay. So now here, the average value is way up here. Okay. The average value is right in the middle, 50%, 80% of VCC, 50% of VCC. Here, 20% VCC. What I've actually done here is I've taken a variable frequency input and created voltage out based on that frequency in. So you can do all kinds of things like that. If I were doing that, I'd probably do a little higher frequency and use smaller filter things to get your average out, but that's the basic idea.
This would be noisy RF line.
Oh, RF, I wouldn't do this RF. Yeah, the 555 timer, because you're using R and C's, you're limited with that. I think, I used to, I in the past, sometimes if I had more time, or if I thought about it ahead of time, I've built oscillators using the relaxation oscillator that we covered in chapter 20. And I've done oscillators using a 555 timer. And you actually find that, especially with the 741, because of the slew rate, really limits the upper frequency that looks nice as a relaxation oscillator. The 555 timer, remember the output was what? It was a flip-flop, right? Not Q, came out of a flip-flop. Very high speed response. This allows very neat, nice looking square waves up to fairly high frequency. But still, RC, you're not going to get much above 1 or 2 megahertz. I haven't tried too hard to see how high I can go with a 555, but yeah. Make sense? All right. Well, unfortunately, phase lock loop is the next thing, but I'll save that for the communications. Come back around in the spring. That's when that will be offered. EET 211. All right. I'm done. I'm done lecturing. Okay. So, hopefully you enjoyed the class, had fun, learned something. Final exam. All online, no lab portion. 50 questions, multiple choice. It will become available at 12:01 a.m. on Tuesday next week. It'll be available all day Tuesday, all day Wednesday, all day Thursday. So basically it goes away at 11:59 p.m. on Thursday. Our official final exam time, I don't know exactly what it is. I don't really care. I always just say it's the same time frame as we meet for class, whatever it is. I'll be here. I'll be here during that time frame. I will take labs, homework, whatever stuff you need to turn in still up through that final period on Wednesday. All right. So I will be here next Wednesday. I'll stick around as long as anybody's around, probably at least 2 hours, because that's how long the final exam period is supposed to be, even though you have 3 days to do. Just a reminder, right? Go in, you can work on it, take a break, log out, all your work is saved, and you can go back in, change things, get back to work, whatever. Until you hit submit, you have access to it.
Available Monday.
Tuesday at 12:01 a.m. Yep, Tuesday. Until Thursday. If you need more time, Larry, let me know. I can always change that. Or if you need it earlier. Do you want it earlier? Or I can make it available earlier too. All right. Any questions? All right. This time is yours.